Yep, thank you. Hi everyone, it's great to be here. So I was asked to give a talk about, well, give a series of lectures on cosmology beyond lambda CDM, which is a huge, huge, huge topic. And so it's really impossible to cover, completely at a summer school. The other thing is that really, although I deal a lot with cosmology on a day-to-day basis, a lot of my background is more in particle physics. So this talk is really going to be focused on kind of particle physics signatures that you can see in cosmology. And so the focus will really be more on having, actually, we'll be thinking mostly in terms of having some kind of non-gravitational interactions. Well, not that the focus will be on this, but I will spend quite a significant amount of time talking about non-gravitational interactions instead of gravitational interactions, which you may be more used to in cosmology. So I'll talk about I'll focus in particular on two different possibilities of cosmology beyond the lambda CDM. One is the presence of extra relativistic degrees of freedom. Um, In this case, you will see that in many cases, we will assume that it really just only has gravitational interactions, and that's what we'll mostly be interested in. And then the other case that I'll be looking into is any kind of new dark sector energy injection or removal into the standard model. Okay, so any process that can somehow end up dumping some amount of energy into any sector in the standard model. Usually we will talk about the electromagnetic sector, so any kind of energy that goes into electrons and photons. Okay, I mean, there are a lot of other scenarios that people talk about a lot in cosmology, especially non-CDM scenarios for dark matter. So things like warm dark matter, ultralight dark matter, and then even on much smaller scales, people like talking about self-interacting dark matter. I don't think I'll have time to talk about any of these things. And also, it's some of the more common topics that come up in cosmology. So you unfortunately probably won't be hearing about that from me. But just remember that they do exist. Okay, so what I'm going to do in the first lecture is to kind of briefly run through the parametrics of these things. What would they do to cosmological evolution? How do we, what kind of signatures do we expect to see from these two cases? And I think that should cover it for one lecture. Okay? So please feel free at any time to stop me and ask questions. The way this lecture will work is that it's very kind of like big ideas, a lot of tilde level calculations and not a lot of details. But the main takeaway is that you know that these things exist and that people work on them, and you can go back and read some more about it on your own time. Okay? So the first thing I'm going to look at is actually number 2. Maybe I should have written this as number 1. Which is energy injection and removal into the standard model. And as far as possible, I will stick to just one example, which is dark matter annihilation and decay. So an example of 2 is if you have dark matter annihilation or decay. Okay, so what does this mean? We have some dark matter, we think dark matter, could be made up of, many different scenarios, but one scenario is that dark matter is some kind of particle, chi. So this is the dark matter. And it can undergo some kind of annihilation process so that, two dark matter particles can come together, and then this annihilates into, for example, E plus E minus, or, anything really, anything in the standard model. So things like B quarks, gauge bosons are possible, and so on. Okay, so we will exclusively pay most of our attention to this annihilation process. There are many other ways in which you can get dark matter energy injection or removal, dark sector energy injection or removal. You can have dark matter being unstable and so it decays into these particles. You could have dark matter baryon scattering, for example, so that would exchange thermal energy between dark matter and standard model particles. You could have oscillations. So for example, photons could oscillate into new particles, just like neutrinos can oscillate and change flavors. There are many different examples of how this can happen, but we'll stick to this one example. Okay. So suppose that this is possible. How would we try to think about, how does the dark matter number density change as a function of time? And so, oh, nice. And so the way that we think about it is that these reactions, like chi to E plus E minus, is characterized by some kind of what we call a thermally averaged cross-section. So we usually write this as sigma V, a thermally averaged cross-section. So this is the one parameter that parameterizes how often these reactions occur. Okay, and so in particular, with these annihilation processes, the rate of change of the number density of dark matter particles is a function of time. For example, in the expanding universe, it will look something like, minus 3hn chi, which is just the usual cosmological dilution. So this is just the dilution factor. This is just the a to the minus 3 dilution. But then there would be an additional term that would look something like minus n chi square sigma v. And then also there's the backward reaction, right? So there's also something that goes like, so this is sigma v of chi to e plus e minus. And then in the backward direction, there would be something like ne square sigma v e plus e minus to chi. Okay? And all the particle physics of your particle physics model that describes what dark matter is, how this annihilation proceeds, is encapsulated in just this one number, sigma v. Typically, when you have two particles coming in, scattering into two final states, we can calculate something called the cross section. But then this cross section in general is velocity dependent, right? It depends on the momenta of the particles that are coming in. And so what we have to do in order to describe some kind of dark matter evolution is that we have to integrate over the distribution of dark matter as a function of momentum. And that's why we have this thermally averaged cross-section. Okay? But I'm not going to go into the details of the particle physics, just that there's just this one number that we're interested in when we talk about annihilations. Okay? So another thing to note is that this prefactor here, n chi squared sigma v, it scales as n chi squared because you need two factors of, you need two particles of chi to come in and react with each other in order to go into e plus e minus, and so that's why there's a square here. But if you think about this setup, which is dn chi dt on the left-hand side, and then this function here on the right, you can see that, if you ask what is the number of annihilations per dark matter particle per time, this is just gamma is equal to n chi sigma v. Okay, so n chi sigma v tells you how many annihilations there are per dark matter particle per unit time. Okay, so how do you think about this? Well, let's look at this equation again. If I didn't have these two terms, right, then I would just have dn chi over dt equals to minus 3h n chi, right? You can do the integration and you see that this is just an a to the minus 3 dilution as usual, right? But if these terms here are big, in particular if they're bigger than this number here, right, then what's going to happen is that you're not going to just get a to the minus 3 dilution. You're going to get additional evolution on top of just the regular dilution. Okay, so what we usually do, what we always do, and what we will see repeatedly in this in my lectures, is that what you want to do is you want to compare gamma to h. Okay, so if gamma is much bigger than h, then what happens is that the annihilation process, like chi to e plus e minus, is able to change n chi a cubed very rapidly. Okay, in other words, the annihilation is able to just remove dark matter particles and change it into a final state that's like e plus e minus, for example. On the other hand, if gamma is much less than h, then we say that the reaction is frozen out. Okay, and in this case, if this was the full, if other than these processes there was nothing else affecting n chi, then n chi would just scale as a to the minus 3. Okay, so just every time you want to see if something is important or not, you compute the rate, you compare it with h, and then this tells you whether it's important to consider the reaction compared to Hubble expansion. All right. Yeah. No, it's not. It's not an assumption at all. It's just that if you look at this term here, you can compare this with this, and if this is important, then you know that these two terms must be there. That's all. Yeah. You'll see a little bit more detail when I talk about how freeze out usually occurs, but usually this. Usually, in the usual way that we think about freeze out and dark matter being in equilibrium at early times, you'll realize that like this tends to shut off earlier than this one because you're kind of going from like less massive states to more massive states. But the point still stands, which is that if you just make this comparison here, then this is an important process to look at, and if it's not there, then it's probably going to go scale as just a to the minus 3. Unless you're in very exotic scenarios that maybe I haven't thought clearly about. Okay. Okay, so one thing to take away from this is that, well, okay, so gamma, the dn chi dt for annihilation scales as n chi squared, right? In here, it scales as n chi squared. So as you go back, earlier and earlier times, you expect this term to be more and more important. And so generically, you would expect that at some point, if you go back early enough, this term is actually really important and you have to put it there. Okay? And if this term is active, then these annihilation processes, chi to e plus e minus and e plus e minus to chi and so on, they are active and they can change the chi number density very rapidly. And so at some point, these very rapid processes will be able to bring dark matter and the standard model into equilibrium. Okay, so since dn chi dt scales as n chi squared, you might expect that at early times, dm and the standard model were in equilibrium. Okay? And then so at early times they were in equilibrium, and then at late times as n chi squared falls as a function of time, you might think that they could fall out of equilibrium. Okay? And so that's the basic setup for what we call the thermal freeze out, which I'll go through now. Okay, so suppose at early times you have dm at t much greater than m chi. Okay, you have dm and the standard model being in thermodynamic equilibrium. Okay, what do I mean by thermodynamic equilibrium? I mean that they are in other words, they're in equilibrium distributions. At common temperature T. And they have a shared, they have equal chemical potential. Okay, equal chemical potential just means that this backward and forward reactions are both extremely fast. So they're much faster than this 3H n chi term. Okay, and you can see that this is something that you might expect because, as I said, annihilation rate scales is n chi squared in this case. All right, it doesn't have to be the case. You can cook up funny scenarios where this, you know, gamma can be greater than H at you know, if you kind of extrapolate back naively, gamma can be much greater than H, but then you can kind of stop this from happening by, for example, not having the universe reheat to a high enough temperature and things like that. Sure, there are always loopholes when it comes to model building, but in general, you would expect that if I extrapolate backward naively, you would expect that they would come into thermodynamic equilibrium. Okay, so if this were the case, when T is much greater than m chi, you know, the temperature is much bigger than the mass, and so the dark matter is relativistic and in thermal equilibrium. So that means that the number density of the dark matter would scale as T cubed, just like relativistic fluids. Okay. And so at this point, since usually kind of T usually scales as a to the minus 1, unless there's some kind of additional heat being injected by other things, you would still get something like n chi being proportional to a to the minus 3. Or in other words, n chi times a cubed being constant. Okay, so if I make a plot of n chi a cubed, then if this is m over t, so that's kind of a confusing thing, but in this direction we have increasing time and decreasing t, right? When m over t is much less than 1, you're basically going to be in a relativistic state and you're going to be kind of flat. Okay? Sometimes people also write n chi over s, which is the same thing. Sometimes people also write n chi over s, where s is the you know, standard model entropy density, which usually scales as T cubed as well. There's a little bit of a difference because there are entropy dumps into the standard model. If you're not familiar with that, that's fine. But for simplicity, you can think of it as n chi a cubed. Okay. So that's the first step. Initially, if everything was in equilibrium, n chi would be proportional to T cubed at early times. Then what's going to happen is you're going to hit a point where T starts becoming less than or equal to m chi. Okay? Now at this point, remember that I have this annihilation process. I have chi going to E plus E minus that is very efficient. And that's why, you know, it's keeping the standard model in the dark sector in thermodynamic equilibrium. So if this process continues to be very efficient when T is much less than m chi, then chi will continue to be in thermal equilibrium. And so that means that, if you think back to your basic thermodynamics, you would start getting n chi being suppressed by a factor of exponential to m chi over t minus m chi over t, because the chi state is just starting to become a higher energy state than, for example, it has an energy of m chi, and so this is just the usual Boltzmann suppression factor of e to the minus et. Okay, so as long as this process is able to keep chi in chemical equilibrium with the standard model, then what's going to happen is you're going to start seeing an exponential decline in the number in n chi a cubed as a function of time. Okay? So that's the second step. And then, of course, at this point, what happens is that n chi is decreasing rapidly. Right? And remember, I said that the annihilation per dark matter particle per time is n chi sigma v. And so as n chi decreases rapidly, this number goes down like a rock as well. And eventually you hit a point where n chi sigma v becomes less than h. Okay? At this point, if you look back at this equation again, these two terms will end up becoming subdominant compared to this. And so you end up with what we call a freeze out, with n chi going back to a to the minus 3 evolution. Okay, so instead of going exponential, instead of going exponentially suppressed, it kind of freezes out at some constant value. And at this point, it will be constant again. Okay, here it's constant. Okay? So the basic picture is as follows. You have some annihilation process. If this rate is large enough that it can bring you into thermodynamic equilibrium at t of less than m chi, then what's going to happen is you're going to get an exponential suppression. And then at some point, that exponential suppression will cut off because you're annihilating so much, and it will end up giving you a level, a final abundance that will then, if there's nothing else happening, then it will just kind of continue all the way down to today. Okay, so this picture is called a thermal freeze out. And it's really interesting because this is one way in which you can kind of have like a predictive way of like theoretically a model that you can kind of control the abundance of n chi, right? So if you think about it, if I have some particle physics model that predicts that this is a process that can happen, then I can go back and say, okay, this is a process that can happen. At early times, I expect dark matter to be in chemical equilibrium with electrons. And so I expect this freeze out to happen. And now I can check, based on that model, do I get the right abundance of dark matter at late times? Okay? The jargon for this final abundance is called the relic abundance. Right? And you want the relic abundance to match the dark matter energy density that you observe in, for example, the CMB. Okay? So based on this process, let's ask what kinds of sigma v do I need to match the abundance that we see in the CMB, okay? And this whole calculation that I'm going to show you is often called the WIMP miracle. And I'll present it sort of at a tilde level which misses some of the details, but then it kind of gives you some interesting insights along the way. So you might not have seen it presented this way. But before I go into this WIMP miracle and trying to ask what sigma v do we need to get the right omega dm h squared. Are there any questions? Yeah. Yeah. Right. Yeah, so I think getting neutrinos to, I think the easier way to do it is for neutrinos to decay into something else, a lighter state. So that reduces the neutrino abundance. And I think that can bring you to, I think it can bring you down to, it can help things, but it can't get you negative. And so it's not quite a solution. It helps, but it's not quite a solution. Yeah, as far as I understand. Yeah. Yeah. Yes. It only works if you only get a freeze out if you are able to maintain this equilibrium when t drops less than m chi. Otherwise, you get something else. Yeah. Okay. If this doesn't happen, then you don't get this exponential suppression. Yeah. Okay. So how do we figure out what sigma v do we need to get the right omega dmh squared, right? So the first thing that I'm going to do is try to figure out what is n chi f, which is n chi at freeze out. Okay, so I know that the criterion for freeze out is when this rate drops below Hubble, and so I know that at freeze out, n chi f sigma v must be on the order of Hubble at the freeze out temperature. And since I'm assuming that all of these things are happening in a very early universe, everything is radiation dominated, and so this is roughly speaking parametrically Tf squared over m Planck. Okay, there's some like 1.66 something square root g star whatever. Okay, I'm just going to drop all those. All right. And for people who don't who are more used to like cosmological constants, it's just that you just have to remember that Gn is roughly Gn is 1 over m Planck squared. Okay, so after the freeze out happens, n chi f, I know that so this is 0.1. After freeze out, I know that it just dilutes as a to the minus 3. And so I can compute what n chi at equality is. So EQ is equality, so that's matter radiation equality. There's a reason why I'm using matter radiation equality, which you'll see in a second. But n chi EQ is equal to n chi f, which was the freeze out abundance, and then it just redshifts as a to the minus 3, t redshifts as a to the minus 1. And so here I can just write that it scales as TEQ cubed over T freeze out cubed. Let me just put tilde, okay? It's tilde because, you know, for example, when you go through the E plus E minus annihilation, then the temperature doesn't just scale as a to the minus 1. But roughly speaking, parametrically, it's correct. All right. Okay. So let me see, where did I get a duster? Oops. Oh, it's just a cloth. All right. Okay. Now I know that the next point is that at meta radiation equality, I know that rho dm is roughly given by rho radiation. Obviously, there's the baryons, but let's tilde level everything, right? So I know that the energy density of dark matter is given by m chi times n chi eq, right? This is just a number density, and the energy density is just given by the mass. And so I know m chi n chi eq is roughly the radiation density at equality, which is parametrically just TEQ to the 4, right? Because radiation scales as T to the 4, as we heard this morning, and at equality, the temperature is TEQ. Okay? And so now I can put this, and this together, and I see that I get something like n chi EQ is roughly TEQ to the 4 over m chi. That's just this thing, which is supposed to be this thing, right? Which is TF squared over m Planck sigma v, right? This is n chi f. And there's a TEQ, there's a TEQ cubed over TF cubed. All right, so this thing is parametrically this thing. All right. And then I know that the freeze out, right? The freeze out starts at m chi roughly t, and it goes exponential, and so the n chi really drops like a rock, and then it freezes out. And so this process here is quite quick. Okay, in some, like, you know, if you do it accurately with the usual WIMP scenario that I'm presenting here, you will find that you know, it freezes out at roughly 20 or so. Doesn't really matter that it's 20. The only thing that I need you to agree with is that TF is parametrically m chi, right? The freeze out happens at roughly when the temperature is roughly at m chi, up to some factors. Okay? Now you can simplify all of this, substituting m chi here, and bringing the m chi over, and simplifying, and you will get the following result, which is that sigma v must be parametrically 1 over TEQ and Planck. Okay? So it's pretty cool. Like, a lot of things fall out. M chi in particular doesn't appear here. So sigma v is actually mass independent in this freeze out case. Like, in order to get the right relic abundance, it doesn't really matter what the mass is. You always need this sigma v. And it also says that the right sigma v is 1 over some geometric mean between m Planck, which is, you know, 10 to the 19 GeV or so, and TEQ, which is 1 eV. Okay, and so you can put in the numbers, and this gives you sigma v roughly 1 over 100 TeV squared. Okay, which is the electroweak, which is close to the electroweak scale. All right, which is where, you know, things like the Higgs and the W and the Z's start becoming important, and the electromagnetic force and the weak force unify. All right. Something about this is really curious, right? Because this depends on some particle physics thing, something that falls out from cosmology. You don't really know why, but then somehow when you plug everything in and you take the geometric mean of these two things, it ends up being the electroweak scale. It's a little bit magical, right? And that's why people call this the WIMP miracle. Because what it says is that if chi goes to E plus E minus or whatever, you know, standard model state is has a weak interaction rate, and by weak I mean the weak force, the SU2 weak force interaction rate, then you will get a right abundance. Okay, and as you can imagine, this is really exciting because we might expect there to be new physics happening at, just above the electroweak scale, because we have other problems in particle physics that need solving by introducing new physics at electroweak scale. In particular, one of the central mysteries of particle physics is that the Higgs is very light, and it seems unnaturally light. And if we could introduce new physics such as supersymmetry at or above the electroweak scale, then we could understand why it's so light. And it looks like if we have a nice dark matter candidate, then we might also be able to solve dark matter at the same time. Okay? So this is really interesting. But if you think about it a little bit more, like you'll also realize that it really doesn't have to be the electroweak scale. And one thing you can do, for example, is that notice that I did everything parametrically, but really sigma v, I should also put in coupling constants. So for example, every time I have an interaction between electrons and photons, for example, the interaction rate scales as the fine structure constant, which is 1 over 100. So there's actually, and it can scale as alpha, it can scale as alpha squared, usually it scales as alpha squared. And in that case, you are down by a factor of 10 to minus 4, just from the fact that electrons and photons couple with a coupling constant that's not 1, right? So really, sigma v, you would expect it to also be proportional to some coupling constant, okay? And if you adjust the coupling constant, if you adjust the coupling constant to what am I trying to say? So if I want it to be 1 over 100 TeV squared, but there's also the possibility that the cross section is actually some coupling constant squared divided by some scale of new physics squared, and I need this to be 1 over 100 TeV squared, right? And so if I want new physics to appear at a lower energy scale, let's say a GeV scale or even an MEV scale, let's say, then really it's easy. All I have to do is just choose alpha to be small. Okay, so the WIMP miracle doesn't mean that it has to be 10 TeV in order to get 1 TeV, 10 TeV in order to get the right freeze out. It just tells you that there is this magic kind of cross section here that you need to hit to get the right relic abundance through thermal freeze out. All right. So numerically, if you do it properly and you put in all the G star evolution and things like that, you will find that this number, so if I do it properly, this number ends up having this magic number 3 times 10 to the minus 26 centimeter cube per second. All right, so that's kind of the target, right? Because really, like, what do we know about dark matter? One of the things that we do know very well is its abundance. And so writing down a model that has this annihilation cross-section will give you the right relic abundance. Obviously, thermal freeze-out is not the only way to do it. There are many papers written about all the different ways that you can produce dark matter at the right relic abundance with all sorts of different mechanisms. But really, it's quite straightforward and it's really quite nice. Okay? Any questions about this? Okay. So what does this do? Like what okay, so now we go like, okay, so there's dark matter annihilation, 3 times 10 to minus 26 centimeters cubed per second. What does this mean for us in terms of looking for dark matter, right? Which is something that we might want to do. So let's think back to this process again. You have dark matter coming together, annihilating into standard model particles. Suppose it annihilates into E plus E minus as a good example. Those particles are just going to be emitted by the annihilation. If your dark matter has a mass in the TeV range, you'll be producing TeV electrons, extremely energetic. And so all of that energy has to go somewhere. And that in turn means that you are going to see an impact of dark matter annihilation on cosmic history. Okay? So the first thing to note is that let's say we have chi going into standard model. If it goes into quarks, if it goes into any other kinds of leptons other than electrons, so if it goes into B, W, Z, any quark, mu or tau, any of these things, the decay lifetime of these things, like the mu decays in a microsecond, right? So all of these particles decay very rapidly compared to cosmic time. So to a good approximation, all of these things will ultimately end up becoming just E plus, E minus, photons, and neutrinos. There are a little bit of protons, but the protons usually don't do much, and it's a very small proportion. Okay, so we can neglect it to a good approximation. All right, but any final state ends up giving you some spectrum of E plus, E minus, gamma, and neutrinos. Okay. Now, obviously, you could go to neutrinos, and those neutrinos, you know that neutrinos weakly interacting, so you can have free streaming high energy neutrinos. Although if the neutrino is above a TeV, then it can actually bram off W's and Z's, and so it can actually deposit energy that way. But if it's sub TeV, then the neutrinos will actually just free stream, and you won't really see them in terms of modifications to the photon baryon plasma, right? And so that's, you can still look for it, and there are other signatures that people look for annihilation of neutrinos, but that is the one exception that I'm not going to talk about in my talk. So the remaining part of the discussion, I'll think about dark matter going into photons, E plus and E minus. And obviously these particles can interact with baryons, right? And so let baryons, both baryons and photons. So E plus, E minus, and photons interact with CMB photons and baryons. Okay, so how do they interact? There are many processes, and it's a mess. Let me just give you some of them. One important one is inverse Compton scattering. And so this is E scattering with a CMB photon going to E gamma, where it upscatters photons. Okay, and so what this will do is that the electron that's coming in, it's at high energies. So imagine a GeV electron, for example, is streaming through the photon baryon plasma, or it's streaming through the intergalactic medium. It will bump into CMB photons, and then it will cool to a lower energy. But then it bumps one of the CMB photons up into a very high energy state. All right, and so that's how it loses energy. And you can already see that this would be somewhat interesting because Well, first of all, you're going to produce a ton of high energy photons. That's one thing. Another thing is that you're going to kick out photons from the black body. And so this can produce spectral distortions, for example, which Julien already mentioned in his earlier lecture. Okay. Another thing that can happen is photoionization. So okay, you have an electron coming in or a positron. It upscatters the CMB to a photon that is maybe a UV photon. Then what can happen is that the UV photon can encounter a neutral hydrogen atom, and then cause it to dissociate. Okay. Let's keep in mind that the ionization potential of hydrogen is 13.6 eV. So that's the ionization potential is 13.6 eV. So any photon that gets bumped up to above 13.6 eV can do this. All right. So remember that the CMB photons currently have an energy of 10 to the minus 4 eV, and so you have to bump them up by 5 or 6 orders of magnitude, which you can do with relativistic electrons. Okay. So what does this do? Well, it produces free electrons. So you get free electrons. Right? These free electrons are also very high energy, depending on what the incoming photon is. It can go around and it can ionize other things. But the basic picture is that you have increased the ionization level. Okay, and if you think about how the CMB was formed, right? The CMB was formed at the point of recombination, when things went from fully ionized to to almost fully neutral with some residual electron fraction. This process would increase that residual electron ionization fraction, and that will have some impact on the CMB as it streams towards us. Okay, and we'll come back to this point later on. Okay, and the last process is just Coulombic heating. Okay, and here I'm just going to draw a picture. You have some high energy electron coming in, and you have some ambient. Remember, there's this free electron fraction that's left after recombination. And what's going to happen is that this electron is going to go in, and then it's going to just kind of jiggle everybody around. And so eventually you end up with electrons that will have more kinetic energy. And so this is just heating. Okay? So 3 different signatures. You could have spectral distortions, you could have increased ionization, and you can have extra heating. All right? It turns out that spectral distortion is not a great way to look for dark matter annihilation, but increased ionization is. And I will go into a rough estimate for why increased ionization is such a great way of looking for dark matter, especially with these kinds of sigma v of 3 times 10 to minus 6 centimeters cubed per second. Heating is also interesting, and I haven't decided yet, but I might explain how to look for extra heating. All right, now, yeah. Yeah, exactly. So what's going to happen is that you get these annihilations, and then they end up producing photons that photoionize things, and then you get an extra. Your free electron fraction is higher than you expected, and then that modifies the CMB that you see, right? Because it's like something that Julien said as well, which is that reionization actually kind of smears out the CMB anisotropies a little bit. This is the same thing, right? You're adding an extra electron, so you're smearing it out in some way, and you can look for that effect. You're smearing it out in a different way, which is good because otherwise it would be completely degenerate reionization, but it's not degenerate. Yeah. Okay. Any other questions? I kind of made this somewhat simple, which is like, oh, okay, there's inverse Compton scattering, there's photoionization, there's coulombic heating, but they're all happening at the same time. And the worst thing also is that it's a cascade, right? Like so the electron scatters one CMB photon, it cools down a little bit, then it scatters another one, and so on. And so it's very complicated, and you have to do all of these things at one go in order to predict, given some dark matter annihilation cross section, given some spectrum that it injects, how much ionization do you actually get? How much heating do you actually get? How much spectral distortions do you actually get? So that's a whole calculation that is complicated but has been done. All right, so this is something that people know about and you can learn about. Yeah. Yeah. Good. Good. So it's not just an SZ effect. Well, I mean, in the usual SZ effect, you have CMB going through a galaxy cluster, and then the electrons are not relativistic, and so that ends up giving a Y distortion. Is the usual story. This is not a Y distortion because it upscatters to very high energies, and it's not Thomson. Yeah. So people have done. There are two things I would say about that. One is you can like compute whether this is something that gives you something observable, and given current constraints, no. It's a little bit too low. In fact, annihilation is not great. Like annihilation doesn't give you that much distortion. Decays is the one that will. But currently, given all current constraints, you're not allowed to have that much decays, and so this signal is actually not going to be that big. But if we do a future spectral distortions experiment, you could potentially see this and set either discover decays or strengthen the constraints. Yeah. Any questions? Very good. So if you produce a photon that's below 13.6, you're not able to photoionize. If you're between 10.2 to 13.6, it's somewhat interesting, and I was obsessed with this for a few months, because if you think about how recombination works, it doesn't recombine directly to the ground state, because that just emits another photon that photoionizes something. It has to recombine to a high end state and then cascade down. And so any photon that is less than 13.6 eV will modify that cascade by a little bit. Again, it doesn't seem like it's very strong, unfortunately, but it's a cool idea. So actually, there was a paper where they looked at dark matter decaying into photons less than 13.6 eV, and they computed the effect on recombination due to the spectral distortion. And they don't get a strong constraint, but they do get something. Yeah. But if you're really, really low energy, then you'll free stream. And if you're produced at like within where Virus has done a measurement, then you would add to the spectral distortions. And so that's also interesting. Or you can even go below that, where people have also tried to do measurements. Yeah. Any other questions? Okay, so what I'm going to do is I'm going to show you why photoionizations is such a good way of looking for dark matter. It's actually one of the best ways to constrain dark matter annihilation, especially for sub-GeV dark matter. So let me just kind of give you an estimate for the size of the effect from, sigma v of, let's say, 3 times 10 to the minus 26 centimeters cubed per second. Okay, so I should be erasing... Which one? This one, right? Yeah. Okay. So again, our starting point is suppose you have chi to standard model with some, and SM is EM interacting, so not neutrinos. If it's, for example, muons, then some proportion of it goes into neutrinos, but then some fraction of it goes into electrons, goes into high energy electrons, and so that fraction counts, right? And with some sigma v. Okay, so I can compute the energy injected per volume per time, right? That is just the number of n chi. This is just the n chi dt. So the the rate of change of the number density of chi times m chi, right? Because every annihilation takes 2 dark matter particles and turns it into 2 m chi worth of energy. And so d injected dv dt is m chi n chi square sigma v. In terms of cosmology, we don't know what n chi is, right? We don't know the number density, but we do know the energy density. And so I should really rewrite this as rho chi squared over m chi sigma v, because rho chi is equal to m chi n chi. Okay? Good. So this was easy. Now the next thing I want to do is I want to find energy deposited per baryon per time. So let's call this dE dt. And if you think about it, it's just very straightforward. It's just take this and divide by NB, the number density of baryons. Okay, and again, I'm going to do tilde level estimates. I'm not going to give you there's no point doing the details because it's much more complicated than this. But roughly speaking, I know that, well, okay, let me just write this out. We know that rho b over rho chi, right, which is equal to the mass of the proton times NB. It's not quite the mass of the proton, but let's forget about helium and all that stuff. But so it's MP n baryon divided by n chi, m chi n chi. And I know that this is roughly 5. Okay, from Planck, let's say. Okay, so you can take this, plug it in here, replace NB with rho B over MP, and then use this relation, and you will get, roughly speaking, that the dE dt is about 5 times MP over m chi rho chi sigma v. Okay, so again, MP is a constant. Rho chi we measure from Planck, right? That's just the energy density of dark matter. And you can see that as I take m chi to be small, this thing can be pretty big. It can get bigger and bigger. Okay, so this gives you a sense that as I go to lower and lower masses, the energy injected per unit time per baryon goes higher and higher. Okay, and so this is going to be a good probe of light, relatively light dark matter. Okay, so now I'm going to find the total energy deposited, the total energy injected, and that's just an integral of dE dt. And I got to be a little bit careful about where I'm integrating from and to, right? So obviously you're not going to get, so I'm going to look at the impact of dark matter annihilation on ionization, right? And so you're not going to get any extra ionization before recombination because everything was already ionized. You're not going to get any change to the ionization level after reionization because everything was already ionized as well. And so you need to integrate from T recombination to T reionization. And if I rewrite this in terms of Z, assuming lambda CDM, then I'm going to end up with this expression: 5 mp over m chi sigma v times an integral from something like 6 to 1100 of dz over h of z 1 plus z rho chi naught 1 plus z cubed. Okay, and rho chi naught is the energy density of dark matter today, which you can also write as 3h naught squared over 8 pi g omega chi. Okay, so you can just do this integral, and you will find yeah, let's just erase this. Do this integral assuming lambda CDM, and you'll find that the energy deposited per baryon, remember E is the energy deposited per baryon, is something like 3.5 eV times sigma V over 3 times 10 to the minus 26 centimeters cubed per second, which is the magic number that I told you about in the wind miracle, and then times GeV over chi. Okay? Now remember that the ionization potential of H is just 13.6 eV. And so what this is saying is that if you have the right cross-section for the wind miracle and your dark matter has a mass that is GeV or less, you're going to dump almost order 1 amount of energy to ionize every single hydrogen atom out there, which is a huge effect, you definitely know. Okay, because that will increase the optical depth by a tremendous amount. Okay, so this is a huge effect, and so you're going to see this. You're going to be able to detect m chi, dark matter annihilation at GeV at this sigma v. And in fact, if you look at the Planck results or the ACT results and so on, it roughly looks something like, if I'm just drawing a picture, there is a line here that is, this is sigma v, this is m chi, and this is 3 times 10 to the minus 26 centimeters cubed per second. And there's a constraint that just kind of looks like this, and the intersection is roughly at about 10 GeV or so. Okay. Now there are some details here, like what is the actual final state that the chi's annihilate into. That changes things a little bit, so it's not really a straight line. There are little wobbles here and there, but that's fine. Roughly speaking, this is what you get. All right. So this is one of the best ways that we have to look for dark matter annihilation in the sub-GeV limit. Any questions about this? Yeah. Oh, I'm sorry. Yeah, you're right. Thank you. You can do this yourself in class. Thanks to Julien, I think. All of this is already kind of put in. You can I'm not sure the level at which it's inside class, but you can definitely put in annihilation. You can solve for the ionization history as a function of time, and then you can compute the impact of the ionization history on the CLs and see how the power spectrum changes. And I probably discuss how it changes the power spectrum later on. Okay. Good. One last remark before I move on. This looks really great, but particle physicists are also very clever. And so you will be like, well, doesn't this kill all dark matter models with sigma v less than, greater than 3 times 10 to minus 26 for sub GeV? The answer is no, unfortunately. You could, for example, have the whole WIMP miracle happening. And so 3 times 10 to minus 26 is the correct number in the early universe. But the sigma v that you get could, for example, be velocity dependent. So if sigma v is proportional to v squared, so if sigma v is proportional to v squared, for example, then the WIMP miracle holds because we're talking about temperatures that are just below m chi, and so your dark matter particles are still, kind of like semi-relativistic going non-relativistic, where v is pretty big. But then, once the freeze out happens, it cools and everything, so that at recombination, remember that like nothing, this extra ionization, you can only see it if the energy is injected after recombination, because that's the only time where you can actually change the ionization level. And so at recombination, you could have V much less than C. This is very easy. It definitely happens if you decouple and then it cools. In which case, sigma V at recombination is much less than the sigma V at freeze out. Okay? So you can still have the WIMP miracle, but then not have the signal. Yes? Yeah. It's a good question. Because if you think about how this goes, yeah, so this scales as 1 plus z cubed, because at the end of the day, this scales as n chi. And so you actually get a much bigger, like the energy per baryon is much larger at earlier times than at late times. And so the effect is mainly happening just after recombination, and then it kind of dies. And this will be different for other processes. Yeah. Any other questions? Yeah. No, very good question. Yeah, no, this is very good. I mean, you're getting into the details here, which is that when we compute um, the energy deposited, right? When I write it this way, I'm assuming that it's only from the homogeneous contribution. If you think about it, at late times it does collapse, and so there is a correction because now there are really overdense regions. And in those regions, you are getting a lot of annihilation. That's true. For the CMB, it doesn't matter because of this 1 plus z cubed weighting, it really favors the energy injection at early times. For decays, it also doesn't matter because for decays, everything scales as number density. And so if it's number density per baryon, you find that everything just cancels. And so structure doesn't really matter. For V squared, that matters. It really does matter. Now, the only thing is that you can't see it, you probably can't see it in a CMB because it's highly suppressed. You do get a constraint, but it's not competitive. Yeah. But yeah, this is a very good point, and you have to include these effects. Yeah. Okay, so what I was saying is that sigma v at recombination is much less than sigma v at freeze out, and so you could have no bound. And this is just one of many ways, many creative ways that people have written down to get out of this very strong constraint. Okay, many things in cosmology are like that. Okay. Yes. Yeah. Yeah, yeah, it's P wave. Yeah, P wave. Yeah. Um, yes, it suppressed the low velocity. So the usual expansion is that you can always write sigma v as like a plus bv squared plus higher order v's. So this is just assuming that there's no constant, which you can get in like um, it just depends on the particle physics, right? Yeah. So like yeah, yeah. Oh, okay, good. Um, yeah, I think I should really write t here, right? Yeah, that's right. Yeah, yeah. Thank you. Yeah. Okay. If there are no further questions, I have 15 minutes, so I think I will just start discussing extra relativistic degrees of freedom. Okay, if there are no further questions. Okay. Yeah. Yeah, good. Um, so yeah, that's a good question. So obviously this is not the only way to look for dark matter annihilation. Um, the other main, most powerful way of doing it for annihilation is to look for, um, you know, chi to any electromagnetic final state in, for example, in gamma ray data. And so you can look at dwarf galaxies. So these are small galaxies, dark matter dominated. So you know that they don't have much, standard model EM radiation. And then you just look at their gamma ray spectrum and you ask if it is consistent with a sigma v of some number. And that's really good for above 10 GeV, which is nice. So there's some limit somewhere here, roughly. I think it goes up to roughly 100 GeV or so. That comes from things like Fermi, which is a gamma ray telescope, HESS, which is a Cherenkov telescope, and so that gets you all the way up to about a few hundred GeV. And then people want to push this to 1 TeV and higher, and a little bit higher, because that's the magic number for a lot of interesting WIB miracle models. Okay, so that's coming. So things like CTA will push this even further. Down here, there are other limits which, as far as I remember, I'm not sure if there have been updates, but as far as I remember, they're all a little bit weaker. And it's pretty cool, like how they do it. So one of these lines comes from Voyager, which is crazy. We basically took the Voyager electron spectrometer data, and because Voyager has left the what do you call it, the heliopause, I think. So the magnetic field is not. It's left the part where the magnetic field shields the solar system from cosmic rays, and so what it's receiving is really cosmic rays from the Milky Way, and so this produces cosmic rays, and so you can ask, is it consistent with Kai to standard model, and set a limit. And I think it's weaker, but it's actually like the strongest limit that we have for dark matter decays in sub GeV. Yeah, which is crazy. It's really crazy. It's super cool. Yeah. Any other questions? Yeah. 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 Yes. Yes. Yeah, that's a really good question. There are many different layers to it. So the first is that at these cross sections that I'm talking about, you can ask like how many dark matter particles actually decay, and the answer is a negligible amount. So it's this is very small really, and it kind of makes sense. Like you've already frozen out, so it means that you're below Hubble, so you're not going to actually change by much. So this doesn't give you any kind of modification to the rho dark matter. But then you could be like, well, okay, what if it decays into invisible states? Um, that's possible, but then you have to remember, like, it's not just the CMB. There's also like, right. So BAO is like lower than CMB right now, and so you could imagine that does something. But then there's also CMB lensing, which goes into the CMB inference. And so if you do that, you also mess with the lensing. And so it's not easy to get it all to work out. And then there are limits on how much dark matter can decay as well, which I think is like, okay, I better not say, but people have studied this to death, and there are some limits on the dark matter decay. Yeah, but I don't think it's very viable because the lensing, like the CMB result comes with the lensing, and the lensing knows about dark matter abundance at late times, so it's not that easy, I think. Um, but if any expert says otherwise, then yeah, yeah, yeah. You could have some subcomponent that decays with a lifetime that is like 1 billion. Yeah, exactly. Yeah, yeah. But I think it's not good enough because there's lensing. Yeah. So lensing knows about omega m at low redshift. So yeah, it's just really easy. Yeah. Yeah. Any other questions? Okay, so I'll do a little bit of extra relativistic degrees of freedom. Um, and then also supernovae is high. Supernovae omega m is high. So yeah. Okay, all right. Well, I work at a place where my colleague is on the shoes collaboration, so I'm biased. Uh, okay, extra relativistic degrees of freedom. So this is the second new physics scenario that I'll focus on. Um, and the idea is that in the dark sector you have something that's very light. It's relativistic today, or doing CMB, or doing BBN, or one of these things. And what happens is this thing adds to. And I'll limit myself to the discussion where this extra relativistic degree of freedom is inert. So it doesn't do anything except just hang out, and then it redshifts with rho goes as 8 to -4, just like a regular relativistic fluid. And the only thing that it does, it just adds to the Hubble because it's an extra component. Um, Now you might ask, like, why the hell would we do that? Well, in the standard model, there are two extra relativistic degrees of freedom that are present: photons and neutrinos. So it's super common, and you could imagine that you build a dark sector. You could have some force carrier that is part of some gauge group that isn't broken, and so it's floating around, and it's some kind of relativistic species, or you could have very light fermions, like in the case of neutrinos. So certainly something that we should study because it can happen in the standard model. Also gravitational waves, yeah, that's true. Okay, so in order for us to understand this, like let's think a little bit about standard model neutrinos. So we'll review SM neutrinos. Okay, so again, I can recycle a lot of the stuff that I discussed earlier on, and that's one of the reasons why I picked this, because I can just keep using it again and again. Um, at high redshifts, and this means when the temperature of the standard model is much bigger than MeV, the neutrinos were in thermodynamic equilibrium with the standard model. Well, it is part of the standard model. I mean, with the EM sector. Okay, by EM sector I mean um, E plus, E minus, protons, and neutrons, and photons, of course. Okay, how was it able to do this? Well, there are weak interactions such as nu E to nu E, as well as nu bar to E plus, E minus. And so all of these reactions scale favorably with temperature. So at high enough temperatures, they go above the Hubble rate, and so they bring the neutrinos into equilibrium. Okay, and you can do the usual exercise of saying, okay, what is the energy density of neutrinos? Well, you know that if it is in thermodynamic equilibrium, it has to have some equilibrium distribution given by density of states given by the Fermi distribution. There are two polarizations per neutrino. This is just for one neutrino. And then all I have to do is just integrate this over energy over the phase space. Okay? And so if you do this, you get the usual result, which is 2 times 7 over 8 pi squared over 30 t to the 4. Okay? 2 because there's 2 spin degrees of freedom. So spin DOF. 7/8 because it's a fermion. If it were a boson, this 7/8 would be 1. And then this is just like kind of like the unit of rho. And so for photons, for example, it's also 2 spin degrees of freedom times pi squared over 30 t to the 4. Okay? Now, so what happens to neutrinos at decoupling? Well, you can kind of ask, like, when does this decoupling occur, which is interesting. So neutrinos decouple. And the decoupling temperature you can estimate, right, by saying, again, the same, I already erased this, but it's the same idea, which is that, let's say we consider this reaction, right? The neutrinos scatter with electrons, and so the rate of this reaction, gamma, should scale roughly as, NE times sigma V. Since NE is relativistic, this scales as T cubed, right? Sigma V is the cross section of this thermally averaged cross section of this thing, but this is a weak interaction, and so we would expect it to scale as the coupling constant of the weak interaction, which is this G Fermi squared. But then to get the units right, I need to multiply. By t squared. Okay, so this is just dimensional analysis, which is that this thing has to scale roughly as 2 powers of GF, which is the coupling constant for the low energy weak interactions, which is the Fermi's constant. And then this is just by dimensional analysis. And then, of course, this has to be comparable to Hubble at the point of freeze out, which is T squared over M Planck. And so you get that T freeze out of the neutrino is roughly given by 1 over GF squared M Planck to the 1/3, which turns out to be MeV, right? Obviously, people do a much better job than this when they do the calculation. So it ends up becoming about 2 MeV. Okay? So at 2 MeV, the neutrinos freeze out, they free stream, and even though they are no longer in thermodynamic equilibrium because they're free streaming, they're not scattering anymore. They still stay in the Fermi-Dirac distribution for the same reason that photons stay in the Planck distribution when they free stream. And so if I erase this. Okay, and yeah, sure. Let me just say maybe one more thing, and then I'll stop. And so I have neutrino decoupling. After decoupling, I can describe everything as with some temperature T nu given by A inverse, with T nu at A decoupling being T of the photons at A decoupling. Okay? Okay. Maybe I can just stop here for now. And then, now I've told you what the neutrinos do. And then the next time we'll come back and I'll tell you what the EM sector does and what that means in terms of looking for, signatures of extra relativistic degrees of freedom. Thanks. Well, they're massless. They decouple at Planck mass. They decouple at high redshifts, and then but they're still there, right? So there's some background of it. Yeah, that's right. Yeah, 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 yeah. Thanks.